Hello everyone, welcome to topic 8.3, weak acid and base equilibrium. By the end of this, you should be able to explain the relationship among pH, pOH, and concentrations of all species in a solution of a weak monoprotic acid or base. Okay, so we're going to focus on these equations given here with the acid and base ionization constants and looking at the equilibrium and how that relates to the weak acids and bases. So, getting started. There are 6 strong acids, as we've mentioned before. All other acids are considered weak acids. When a weak acid is dissolved in water, only a small amount of ionization will occur according to the general equation given below. There is an alternate version of this that you might see where we look at just the acid dissociating because we assume it's already in water. That releases the hydrogen ion and the conjugate base. But if we add water here, the hydrogen ion is still present over here, and we're just omitting the water. This equation, though, is the most correct because it does fully represent what is going on in solution and is also what College Board or the AP test will use as well. So the equilibrium constant associated with the reaction shown above is designated as Ka, and this is called the acid ionization constant. Since these constants are generally very small, the pKa is often reported instead of Ka. For acids, the smaller Ka results in a larger pKa and is thus a weaker acid. A weak acid will exist primarily in its molecular form or unionized form in solution as shown in this molecular model, where we see the hydronium ion here, the conjugate base here, but all of the unionized weak acids still stuck together. So notice that most of the weak acid molecules remain intact and only a few ionize. The weaker the acid, the less ionized particles there are in the solution. Looking at weak bases, we have strong bases, which are group 1 and 2 hydroxides, excluding beryllium and magnesium hydroxide. All other bases are considered weak. When a weak base is dissolved in water, a small amount of the base will react with water to produce hydroxide according to the general following equation. Note B represents any base, not just the hydroxides. So the equilibrium constant associated with the reaction shown above is designated as Kb, and this is called the base ionization constant. Since these constants are generally very small, the pKb is often reported instead of Kb. For bases, the smaller the Kb, the larger the pKb, and the weaker the base. So this follows the same trend as the acid ionization constant. A weak base exists primarily in its unionized form in solution as shown in this model below, where we see the base here, and this is unionized because it hasn't accepted the hydrogen ion. And then we see some of the hydroxide and some of the conjugate acid, but not a lot because it is a weak base. So percent ionization is a measure of the extent of the ionization of an acid. A strong acid will have a 100% ionization, while weak acids will have much lower percent ionizations, which can be calculated using the equation given below. Percent ionization is dependent upon both the strength of the acid or base and the initial concentrations. If acids are of equal concentration, the weaker acid will have a lower percent ionization. If we have 2 samples of the same acid but at different concentrations, the solution of lower concentration will have a higher percent ionization. This is kind of like related to the common ion effect. So let's look at an example. The pKa of hypochlorous acid, HClO, is 7.54. What is the pH of a 1 molar or 0.1 molar solution of the acid? So we would start by writing our dissociation expression. So writing the chemical equation for the dissociation of hypochlorous acid So the acid reacts with water, and it's an equilibrium process to form the hydronium ion and hypochlorite. As a reminder, this is the acid and conjugate base. This is the base and its conjugate acid, just to kind of like review a little bit. Okay, so the other thing we need to know is the Ka, because the pKa is not going to be much help when we write the equilibrium expression. So we know that Ka is 10 to the negative pKa, because I'm doing the log. And so if we calculate that, this is 10 to the negative 7.54, and this ends up being 2.9 times 10 to the negative 8. We also know that the equilibrium constant expression for this is H3O plus the hydronium ion concentration times the hypochlorite ion concentration divided by the concentration of hypochlorous acid. And so now we are ready to set up our ICE table. Because it involves K, this is an equilibrium problem, so we will use an ICE table. Okay, in all ICE tables or equilibrium problems, we don't look at liquids or solids, so I can cross off water. Our initial concentration of the hypochlorous acid is given as 0.1 molar. Before anything dissociates, these are both 0. So we know that this is going to be minus X, and these will be both X. So we have X, X, and 0.1 minus X. Okay, so we can substitute all of our known values into our equation and solve for X. So 2.9 times 10 to the negative 8 is our Ka value, and then we have H3O plus, which was X, times the hypochlorite ion, which is also X, all over 0.100 minus X. Because the equilibrium or acid ionization constant is so small, we can approximate this X to be about 0. You could also use a solver function in your calculator. So then we simplify and solve for X, and when you solve for X, you should get 5.4 times 10 to the negative 5 molar. Well, that X is equal to the concentration of the hydronium ion from our equilibrium ICE table box above. So we can then calculate the pH of this solution, because that is going to be equal to the negative log of the hydronium ion concentration. And solving for this, or plugging it into our calculator, you should get 4.27 for the pH of this solution. Okay, so let's look at another problem, and this space was in case you needed more space to work it out. Another example problem for this, calculate the percent ionization for a 1.55 or 0.155 molar solution of acetic acid, where the Ka is 1.76 times 10 to the negative 5. Well, your first step is to always write the reaction equation. Oops, I can't count or read. So the weak acid reacting with water and its equilibrium, so make sure you're writing that. And this is going to be H3O plus aqueous plus the acetate ion. Okay. And then your other job is to also write the Ka expression, which I'm going to put over here and tuck it in, hopefully. So H3O plus times the acetate ion, if I can fit it in, divided by the concentration of acetic acid. Okay. And so now we can set up our ice table where the water isn't counted, and these two start off at 0, so we know we're going to make them. And this was given as 0.155 molar, so 0.155 minus x. So plugging everything into the Ka expression, we have 1.76 times 10 to the negative 5 is equal to x times x over 0.155 minus x. We can simplify this a little, and solving for x, you should get that it is equal to 0.00165 molar. And so since we want to calculate the percent ionization, this is also equal to the hydronium ion concentration. So we're going to end up using that in our percent ionization, which is the amount of acid that ionized divided by the initial concentration of the acid. So how much from the total, this is how much from the total ionized. And since it's percent, you have to also multiply by 100. So plugging this into the calculator, you should get 1.07% ionized. Okay, so using the equations and the concepts covered here and in previous sections, complete the you do, check your work, and thank you for tuning in.